Cyclic Isomers of heptane, C7H14. The formula C7H14 indicates 1 degree of unsaturation. In this video, we will focus on the saturated ring structures, known as cycloalkanes. Isomers will arise from different ring sizes and various branching patterns. We have a separate video for the alkene isomers without ring in the link below. Our strategy is to systematically decrease the size of the carbon ring and explore the possible branches for each size. Case 1, starting with a 7-carbon ring. With all 7 carbons in the ring, there's only one possibility. This gives us cycloheptane. We add the remaining carbon as a methyl group. This forms methyl cyclohexane. All positions on the ring are identical, so there is only one isomer here. Case 3, a 5-carbon ring with 2 carbons as branches. The 2 carbons can be a single ethyl group. First, we can add the 2 carbons as a single ethyl group, giving ethyl cyclopentane. Alternatively, we can add them as 2 separate methyl groups. Placing both on the same carbon gives 1,1-dimethyl cyclopentane. Placing them on adjacent carbons gives 1,2-dimethyl cyclopentane. And placing them on carbons 1 and 3 gives 1,3-dimethyl cyclopentane. Case 4, a 4-carbon ring with 3 carbons as branches. The 3 carbons can form a single propyl or isopropyl group. First, as a straight chain propyl group, or as a branched isopropyl group. The carbons can also be split into multiple branches. For example, 1 ethyl and 1 methyl group, or even 3 separate methyl groups. Case 5, a 3-carbon ring with a 4-carbon branch. The remaining 4 carbons can be attached as a single butyl group, which itself has 4 isomers. First, the straight chain N-butyl group. Next, the isobutyl group. Then, the sec-butyl group. And finally, the tert-butyl group. Many other combinations of smaller groups also exist. We have found these 18 representative cycloalkane isomers by systematically reducing the ring size. Many more, including stereoisomers, also exist.